morning. So welcome. So we're going to talk about current and resistance. And so I'm going to flash through it so you see where we're going, and then I'll come back. So we're going to start talking about current, and we're going to find out it's the rate of flow of charge in time. And we're going to find out that the charge does not go in a nice path like water flowing down a stream. It's quite, it's a random walk, really. Well, it's a random walk with a little bit of field superimposed on it. We're going to develop this thing called a current density, which frankly, I don't use that much in my day-to-day life. It comes up later on, but the thing you've really got to get comfortable with is current, I, rather than J. And then we'll develop ideas about conductivity and resistance. And frankly, I deal a lot more with resistance than I do with conductivity, but we should know what conductivity is. And then we talk about resistivity a lot. And then we're going to talk about the conceptual ideas about how things actually do conduct. And we're going to talk about the temperature dependence of resistivity and resistance. And then we'll talk about power. And I think that's about it. So, fair enough. We're not going to get into complicated circuits or simple circuits. We're just building the basic idea. A few analogies. I think of current like water flowing through a pipe. So in my mind, I think of water system. So here's a pump, and there's a big pipe. The last thing you want is a pump connected to a small pipe, because it's like trying to blow air through a straw. And then we take it over the top and we bring it down here. And we take it to the bottom and we bring it down here. This pipe is so thick that it really is not affecting the flow. It's like just directing where the flow goes. But then in my important bit, I connect components, and the components might be regarded as being straws. And there might be, I don't know, there might be a series of them. And I can picture them like this, where I might have two of them, and I might have like that, and then and to my mind, that is this circuit. I have a power, a battery. I have one resistor. I have another resistor. I have another resistor. Can you see the analogy between those two drawings? So ironically, the wires, which we draw as just a very thin line, they're like big, wide pipes. And then the resistors, which we draw as squiggly lines in the United States anyway, they are like the thin straws. And clearly, you gotta, this pump is going to cause a water pressure. And if this is a water pressure, let's say this is 0 psi, pounds per square inch. And let's say this is 60 psi. So that's what the pump does. It kind of, where on my diagram, if I say A, B, C, D, E, and F, it's not F. So vote, please. Where do you think the 60 psi will be on the right-hand side of that diagram? Will it be at marker A? Will it be at marker B? Will it be at marker C? Will it be at marker D, etc.?
The clickers only have A through E.
That's what I'm saying. It's not F.
He's giving you a freebie. What was the question again?
So where would the 60 psi, if I was to say, oh yeah, we're going to get 0 to 60 psi on the right-hand side as well, where would you picture the 60 psi as being applied? At level A, at level B, at level C? Where do you think? So where do you think this will be applied? Let that go. I'm going to turn this light. I'm sorry I didn't realize these lights were on. So how are we doing? Not bad, 14 or so. Let's get a couple more. If you don't want to answer, just put down E. So stop, and let's put down that. And most people are saying A, and that's the truth. There's no pressure drop across a thick pipe. It's like it's just there's no constriction. So this would be 60 psi here, and I'm going to tell you that the 0 psi would be down here. Now, let me ask you another question. This is going to be a true or false. True being A, false spin B. There is no pressure difference between B and C. Is that true? If it is, press A. If it's not true, press B. There's no pressure difference between B and C. Is that true or not true? There's no pressure difference between B and C. Big thick pipe, no pressure difference between B and C. Is that true or not true? Let's have a look. So split actually. So let me ask you, for somebody who says that that's not true, who says there is a pressure difference between B and C, so do you mean to say that there's a small but tiny, or do you mean to say, no, it's quite measurable? What do you think? Anybody who said B? So why did you put down B? What was the rationale?
I think it's measurable.
So, but what about in a theoretical system, would you? Oh, we're talking about PSI. We're talking about water flow, and we're talking about pressure in water.
I don't see the difference.
Okay. Well, so there is no pressure difference between B and C, and it doesn't matter about the water splitting. It doesn't matter. What matters is there like a higher pressure there than there, and because it's a big thick pipe, the assumption is no pressure difference. So all the pressure difference is across here, across there. And all you can say at this point is that between A and F is 60 psi, because that's what you're applying across the system. I can tell you between B and C there's no pressure difference. I can tell you between D and E there's no pressure difference. Let me ask you a question. If this is number 1 and this is number 2, 3 choices. Pressure difference across 1 is bigger than the pressure difference across 2. Pressure difference across 1 is equal to the pressure difference across 2, or pressure difference across 1 is less than the pressure difference across 2. What do you think? A, B, C. There you go. I'll let you get started. So if you were to get a pressure gauge and you were to put it between the top and the bottom of straw 1, you'd get a reading. If you were to put the pressure gauge now between the top and the bottom of straw 2, would you get the same reading? Would one be bigger than the other?
I'd say the same.
So, but, okay, so let's have a look. Stop. Most people are saying the same, and yeah, it's the same. Now, that happens whether or not the straws are the same width. I could have a quite thick straw letting a lot of water through, and a tiny straw letting very little water through. The pressure difference will be the same. Maybe the water flowing through them is not the same, but the pressure difference is the same, because this is a nice thick pipe, so you can't have a pressure difference between there and there, and you can't have a pressure difference between there and there, so they must be the same. If I look across here, and I have 6 volts, then we can see that the potential difference between A and F is 6 volts. Agreed? And I can tell you between B and C, there is no potential difference. It's wire. In theory, I'm sure there's a tiny little bit, but we deal with, in practice, if you measured carefully, there's a tiny little bit, but we deal with theoretical wires, perfect conductors. And I can tell you that between, I'm going to call this E, F, G, between G and C, no potential difference. And I can tell you the voltage drop, the potential difference across this resistor is the same as the potential difference across that resistor. Let's think in terms of current now. The amount of current flowing out of my battery is I amps. Can you tell me how much current flows through this first resistor? I amps. It's got nowhere else to go. Current is like traffic on I-4. Cars don't disappear. I've looked. They don't disappear, and they aren't created. They're just like, if you enter, you stay on until you leave. So any current going down this wire has to go through the first resistor. Any current going through that system has to go through the last resistor, has to go through the resistor at the bottom. Any current going through that wire has to return to the battery. What I can tell you about is in the middle bit here, the total current going through both these resistors added together is the same as I. So, I. Now, I got to somehow add these two up to get I, and we'll get to that later. Okay. So, in all this stuff, we tend to talk about potential difference, EMF, we call EMF, often we call it like that. EMF, potential difference, current and resistance. So that's where we're going to go. There's another term which is resistivity, which we'll get to. Okay. So definition of current. Current is the rate at which charge flows through a surface of area A. So here's a wire, for example. And imagine it's got a cross-sectional area. We're saying how much current flows through it, how much positive charge flows through it. And we call that current. Average current is the delta Q over delta T, or dQ by dt. It's that triple line means it's defined as. We're saying that. Current is measured in amps or ampere, named after ampere. And 1 amp is 1 coulomb per second. So 1 coulomb of charge flowing through a cross-sectional area in 1 second is an amp. An ampere is a huge amount of current. Well, it's a lot of current. Okay. A typical household supply, something like, what would it be? 100 amps?
200 amps.
Nice new house. In my old house, I had a little house in South Tampa. It was like the bachelor house. I had a 100 amp power supply. We put an extension on it. We had to get 200 amps. So that's typical. Okay, so an amp is a coulomb per second. Direct current flow is taken to be the direction of the flow of positive charge. I know it's the electrons that are flowing, but it doesn't matter. It works just fine. They guessed before they knew, and it still works, so why bother messing with it? So now we're going to do something a little bit, it's kind of interesting in a way, but frankly, it's a material science interesting rather than I'm building a circuit interesting. It's like that. We're going to picture a wire. We're going to picture some charges in it. We're going to have a certain section of the wire. So if we got a kind of section that looks like that, and there's current flowing through it. We say let little n be the number of mobile charge carriers per unit volume. So what on earth does that mean? If I have a piece of wire, it's got atoms all over the place. It's got electrons in all of those atoms. They're not all free. The ones on the inside are pretty well tied to that atom. It's the ones on the outside that are free. Some materials don't have free ones even on the outside, and that would be a ceramic, for example. Doesn't easily. The atoms, the electrons even to the outer shell tend to be pretty well attached, covalently bonded, you know. Other materials, ionically bonded, I'll give you an electron if you give me the space for the electron. Yeah, other ones are kind of like very loosely bonded, and they're the so-called metals, metallic bonding, where the electrons in the outer shells don't even know which atom they're in. They're kind of like just drifting around the material. Okay. So how many of those do you have? You know, not every atom, but not every electron, but how many can you get shaken loose? That's n. For aluminum, you'll have one value. For gold, you'll have another value. For zinc, you'll have another value. That's all in a book. Engineers know about that. Physicists, I know that n exists. Engineers, I actually know where to find the value of n. It's like, you know, who do you want fixed in your car? You know. So n is the number of mobile charge carriers per unit volume. So here's a unit volume, 1 meter by 1 meter by 1 meter, and I got n of these little mobile charge carriers in there. Delta Q will be the charge in the section being considered. So delta Q is all the charge inside here, and Q is the charge on each charge carrier. So if I have a little charge carrier, there's n of them, and it's got a charge of Q. So now I'm going to play with this. The total amount of charge inside this cube will equal the number of charge carriers per unit volume times the volume. And the volume is the cross-sectional area times whatever the length of the wire is, times Q. So that bit there tells me how many charge carriers I deal with, and that bit there tells me how many coulombs each charge carrier carries. Okay? So then we say, well, let's picture what's going on here. And what we have is, have you ever been to the fair and you have this machine? Man, I wish I'd invented this machine. It's basically a whole bunch of nails nailed onto a board. And then underneath you have a bunch of trays. And the way it works is you put your money in up here, and if it falls in one of these, I'll give you your money back and tell you what a winner you are. And if it falls in any of those, I'll keep it and say, bad luck, try again. Okay? So I mean, we might as well just use a weapon, you know? It's just like, so what happens, this guy hits and it bounces and hits and bounces and hits and bounces and hits and bounces and hits and bounces, and then, you know, oh, I'm sorry you lost. And the reason why we like it is because we like the feeling we get during that time. I mean, if you just said, here's the game, give me your money, you wouldn't play. But if I said, here's the game, throw your money towards me, and oh, you're going to get it back. No, you're not going to. Yes, you're going to get it back. Then you'll do it again because it's exciting. So that's the game here. It's like using gravity and these pins to kind of like, that's exactly what happens here. The charged particle, it's an electron. So it's going to go in the opposite direction to the electric field. So it's accelerated downwards like a boulder is. And it hits, and then it does a projectile bit and hits again. And it does a projectile bit and hits again. And does a projectile bit, hits again. Projectile bit, projectile bit. Oh, man, really hit. So its actual speed is really high. It's flying along, but its velocity, average velocity, not very high, because it's what's called a random walk. It's kind of like every time it hits something, it kind of goes off in some random direction. So it's not going to go straight. So its speed is much numerically higher than its velocity is. So we talk about a drift velocity. VD, drift velocity. So we say, okay, this is the amount of charge I have in my little section of, so this is the amount of charge I have in my little section of wire. Let the drift velocity be the drift speed of the charge carrier. So that means that the charge is equal to N. And rather than saying delta X, I'm going to say my drift velocity times delta T. Yeah, velocity times time is like distance. So I can just substitute in A times drift velocity times T for that A times delta X times Q. And then I recognize, oh, hold on. My current is my charge per time. So divide this thing by my time. And I go, well, N's there, and Q's there, and A's there, and my drift velocity is there. But that goes away because of that guy. So I get NQ drift velocity times A. Let's think about this. As I increase the number of charge carriers per unit volume, my current goes up. Agreed? That makes sense. Better conductor, more current. As I increase the charge on a charge carrier, well, they're all really electrons, so can you really play with that? But if you could have more charge on each charge carrier, then yeah, you'd get a better deal. If you could make the drift speed double, you'd get twice as many charge carriers through per second, so your current would increase. And if you had twice the thickness of the wire, twice the area of the wire, like twice as many lanes of traffic, I'd expect this to go up. Got to be careful with that. If we go to AC, then the area of the wire is not exactly the area that your current chooses to go through. But at DC, you can pretty well assume that it is. So let's rearrange this. So my drift velocity is equal to the current over N times Q times A. If you put in a typical current with a typical number of charge carriers and a typical charge on a charge carrier and a typical area for a typical piece of wire, you get a drift velocity measured in millimeters per second. So when you turn a light switch on and the light lights, that electron that you let through that switch does not have time to make it to the light. It's like a bicycle chain. There's a little link there. And when you start pedaling, that link does not suddenly have to be on the back wheel causing it to turn. That link pushes, if you like, the one in front, which pushes 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 the one in front, and so on. So they all move together. And so all the electrons in a circuit move together. If I can move one of them, I can move all of them, because they're all in a big chain. That's why lights come on basically instantaneously. You switch the light comes on. Because there's electrons already in there waiting to be pushed. Okay. So, let's talk about current density. Current density is the current per area. Well, we know that the current is NQVDA. So the current density is NQVD. Okay. I do not expect you to know that equation. Know of it, know what the letters stand for, but don't remember it. Okay. current density J and electric field E are established in a conductor when there is a potential difference across the conductor. Okay. So for ohmic materials are kind of like wires, graphitic materials, that kind of thing. For ohmic materials, the current density is equal to this thing here, which is my conductivity, times my electric field, where sigma is the material's conductivity. Let's have a look. Electric field equals my potential difference over my L. That's an L. I'm sorry about that. That's an L. It's getting confused with an I, so just be careful about this. There's a reason why we don't want to use big L in the notes, because the next chapter's on, well, in a couple of chapters we're on inductance, which is L. So we really are in a mess for letters. Yes?
Can we use cursive L for these?
I suppose, yeah. Why not? Yeah. So remember what we said? We said E is equal to, we said, yes, E is equal to volts per meter, delta V over delta X. Remember we did that last time? So that's where that comes from. So, and J is equal to I over A, so delta V is equal to EL, which equals, where am I going with this? Delta V is equal to EL, I just got that from there. Delta V is equal to EL, and I'm not seeing it. And E is equal to J over sigma, so that's J over sigma times L. That's L. Which equals L over sigma times A times I. So that's L. So what have they done there? They've taken that J and then they've said, where does that come from? Sigma L. Oh, I is equal to J. J is equal to I over A. So I'm sorry about that. It's like it's a way of getting to this expression. Delta V is equal to L over sigma A times I. Okay. We can define resistance such that L over sigma A is equal to R. So that's my resistance. Don't care about that. Don't care about it. That is like golden. You're going to use this all the time. So just, I got there from this. So delta V, which is like water pressure, is I, which is like water flow, times R, and R is like the resistivity, or I should say the resistance, the thinness of my straw. If I plot a graph, I've got to be careful here. We, by tradition, put the independent variable horizontally. You can adjust V. You get whatever current the system decides. I is your dependent variable. And when we plot those out, we get a straight line. And a casual observer will say, oh yeah, a straight line, it's the slope. Oh yeah, that's the resistance. It's not. I is equal to 1 over R times delta V. Just like Y is equal to mx. Look at that. I is the Y, not the x. Delta V is the x. So watch out for that. A high resistance resistor has a shallow characteristic, and a low resistance resistor has a steep characteristic. Just don't be casual about that. Just set an alarm bell. It's not as trivial as it might at first seem. This is Ohm's law, and it's used like all the time. So my dad was in the Air Force as a kid, and I told you, didn't I? Did I tell you about that? He failed the test to be a pilot, so he said, "What happens now, Sergeant?" And the guy said to him, "Well, you either, in a week's time, we're going to give all you guys who failed the pilot's test a test, and if you pass it, you go to navigation school, and if you fail it, you go to gunnery school." And navigation school was 18 months, and gunnery school was about 4 days. And the life expectancy for a rear gunner at that time in the war was 6 hours in the air. And you know that we're going to give you the rear gunner's job, because that's where they needed people. So my dad said, because I was complaining about the pressure of exams, and he goes, you think you got pressure? I mean, imagine a test where if you pass it, you have 18 months of college, and if you fail it, you get a week, and then you're probably going to have a couple more days. And so he passed it. So, or else I wouldn't have been here. He passed it, and it changed his life. He got basically college from he was working class. There was no way he was going to college. And he got introduced to so many things. He was a lifelong amateur radio fan, and he learned his circuitry in the Air Force, along with his navigation, his vectors, and all that kind of stuff. He learned it all in the Air Force. And he was telling me about, I was talking about Ohm's law, and he said, "Which one?" And I said, "What are you talking about?" He goes, "There are 3 Ohm's laws." And I said, "No, Dad, there's only one." And he goes, "No, there are 3 Ohm's laws." So eventually I said, "Prove it." And he goes, "First Ohm's law, V equals IR. Second Ohm's law, I equals V over R. Third Ohm's law, R equals V over I." And I'm like foaming at the mouth saying, "Dad, that's called algebra." And I realized they were teaching guys who had very little formal schooling to do circuits. And it's the most brilliant thing out. You don't have to teach them algebra, just teach them the 3 forms of Ohm's law and tell them to get on with it. And he proudly got on with it. So it's kind of amazing. But we're going to use this circuit over and over again. So really take it to heart. There is a thing called resistivity, and formally resistivity is 1 over the conductivity. But frankly, we use resistivity far more than conductivity. Resistivity is the property of the material. The analogy is if resistance is to resistivity the same way that weight is to density, ironically also done with a rho. Mass. Mass is about the sample. Resistivity is about the material. Resistance is about the sample. Resistivity is about the material. So resistivity is a material property like density is, whereas resistance is a sample property like the mass is. So if I look at the linking equation, and please know this cold, is R is equal to rho L over A. L is the length of the resistor, and A is the cross-sectional area. And that works nicely for a cylindrical, this kind of shape. If I had a tetrahedral-shaped resistor material, I'm not sure what the equation would be, but for a cylindrical or a nice long tube kind of thing, it's going to work out fine. So here's some examples. We've got just a few minutes, haven't we? What is the resistance of a cylindrical resistor that is made of a material that has a resistivity? So the resistivity is equal to 4 ohms. Am I right on that? 4 ohms per meter? R equals rho L over A. So rho is equal to RA over L, which as far as I can see is ohm meters, isn't it? Yeah? So this is, that's not right. It's ohm meter. So the resistivity is 4 ohm meter. The length is 3 meters. Cross-sectional area, this is where I can mess with you, 0.2 square meters. We say R is equal to rho L over A. R is equal to rho, which is 4 times L, which is 3 times A over A, which is 0.2. So R is equal to 12 over 0.2, which will be 60, won't it? 12 over 0.2 is 60. Is that right? I think that's right. 60 ohms. Let's just stop for a minute. You know I'm going to mess with you. Put yourself in my shoes. What am I going to do to make this more interesting? I'll give you the radius rather than the area, so you'd have to use pi r squared. What else could I do? I could give you the diameter, which is like messing with you just a little bit more, yeah? What else can I do? No, I wouldn't do that. No, that's like, just in terms of, just look at your equation and look at your numbers. I can mess with your prefixes, and you know that if you get the prefixes wrong, I got no sympathy. This is physics 2. This is my last chance to make sure you go away and make us proud. Okay? So, you know, expect something obscure like micro meters squared, you know. I'm going to mess with you on that. I'm going to test you on stuff like that. A resistor has a resistance of 6 ohms. What is the resistance of another resistor? Oh, okay. The international system for resistors is that, actually. I don't know. On a circuit, these days, if you get a wiring diagram for, say, a motor or an instrument or a... I know if you get a Honda car, if it's the manual that comes with a factory, it's going to have the international system. But do you, for those of you who have done some of this, which do you see more often? Do you still see the squiggly line, or do you see still the squiggly line? Okay. But if you see squares all over the thing, it's standing for resistors. So this is one of these ratio problems. So this is 6 ohms. What's the resistance of another cylindrical resistor if its resistivity is doubled? So we go what is the resistance? So R new over R old equals rho new L new over A new over rho old L old over A old. And you play this game where you say R new over 6, because you know what that is equal to, and you say the resistance of another resistor, if the resistivity is doubled, so that is twice what that one is, and the length is tripled, so that is 3 times what that one is, and the cross-sectional area is a half, so that is a half what that one is, and that, my friends, is equal to 6 over a half, which is 12. So Rn is equal to 72 ohms, not 12 ohms. It's such a pity when people don't bother writing that down. They put that down and they forget to multiply it by the original resistance. I'm going to stop it there, and next time we're going to talk in terms of some conductivity stuff. So I'm right, aren't I? We end now, yes? Yeah, so I'm going to stop there and we'll continue next time.